Okay, so let's talk about Cauchy sequences. So let's start with just kind of the definition, which I have written at the top here. And this is just that a sequence A sub n is Cauchy if for every epsilon value greater than 0, there exists a big N such that the absolute value of A sub n minus A sub m is less than epsilon for every n and m greater than n. Now, before we get into actually proving that sequences are Cauchy, let's just try to digest what this definition means and kind of figure out what the importance is. Because if you kind of understand why you're using this, it makes it a lot easier to write the proofs to prove something that is Cauchy, in my opinion. So let's just start with what the importance is, and I have it written right below the definition of what a Cauchy sequence is. So really, the power of Cauchy sequences comes from another theorem, which states that a sequence converges if and only if it is Cauchy. And I'll actually do a proof of that theorem in another video. But that is really the utility of proving that something is Cauchy. So whenever you're going through and you're trying to prove things are Cauchy, remember that's ultimately the reason why you're doing it. Because if you remember from some previous problems you've probably worked in your analysis class, whenever you were trying to prove that a sequence converged, you always had to do like the epsilon L thing, where you had like the A sub n minus L, and you had to find an L. So you already had to know what the limit was of a sequence and then prove that your sequence converged to that limit. In this case, you can prove something converges without ever having any idea what that L value is. And so that's really the power of using a Cauchy sequence. Now, before we actually get into proving something, let's try to digest this definition. Now that we understand why we need to know Cauchy sequences, let's try to figure out what the definition means. So again, like always, you're almost always going to start with this for every epsilon greater than 0. And again, epsilon's arbitrary, so you can continue to make epsilon extremely close to 0. It can never be 0, but you can make it infinitely close. And as you make that delta, or the epsilon, infinitely close to 0, you're bounding this A sub n minus A sub n term in absolute value. You're bounding that to make it extremely small as well. So the smaller your epsilon is, the smaller that difference has to be. And the point of a Cauchy sequence is that you want to find some large n value that forces the little n and little m to satisfy this property right here. Now, what does that mean? Let's say you have a sequence, and let's say A sub 1's right here. So the first term of your sequence is right there. Let's say the second term of your sequence is right here, the third one, the fourth one, the fifth one, the sixth one, and so on and so on. This can go on for a really long time. But eventually you're going to get to a point, if your sequence is Cauchy, you're going to get to a point where these start to get closer to each other like this. You'll get to a point where they look like they all converge to one spot. And what you're doing whenever you prove something is Cauchy is you're trying to find the n value that causes this to happen. So if something is Cauchy, that means that you at some point in the sequence, at some value of n, you get to a point where the difference between the terms, so the nth term and the mth term, they converge to the same spot. That's ultimately what you're doing with this. You're trying to find where these values converge to. And actually, I stated that wrong. You're not really figuring out where they converge to. You're just figuring out when they converge. So you just want to find that value of big N that causes the terms of the sequence to converge together.